Hello, students. So let's try to solve the following questions about balls and urns. Suppose we have 15 identical balls and let's say we have 6 distinguishable urns. Maybe they're labeled, maybe they're all in a row, so we could tell which one's in first from the left and which one's, which one is which, like that. But in any case, we have 15 identical balls and 6 distinguishable urns. And let's take a look at what would happen if we first said no urn may have less than 2 balls. Well, okay, for a problem like this, all we have to do is say, okay, well, each of the urns has to get 2 balls. Let's place those first. The balls are all distinguishable. So at that point, I don't have to worry about which balls go in the urn. I just put 2 in each. So that means I'm going to have how many left? I'm going to have 3 balls. So it's the same as placing 3 identical balls in 6 distinguishable urns. And then it's a stars and bars argument where I get 3 plus 5. Choose 5 as my answer. Very simple. Okay, so now, same situation, but what I really want to ask is, instead of giving it a lower bound, I want to give it an upper bound. So I'm going to say no urn may have more than, and let's see, let's make it 4. No urn may have more than 4 balls. Okay, so it's certainly possible, because if I had four balls in each urn, I'd have 6 times 4, which is 24 balls. So it's definitely doable. There are solutions to this problem. But how would I solve it? 15 balls, 6 urns. No urn may have more than 4 balls. So that's a bad condition. So let's break this up into sets where this goes wrong. And then we want to remove that union. So what I could do is I could say AI is the condition that it's the set of distributions with, or I should say, where with urn I having 5 or more balls. Okay, so if I can avoid A1, A2, A3, A4, A5, and A6, I'm good. So I want to get rid of that union of these sets. I want to remove them. Okay, so this is a perfect example for inclusion, exclusion, but I have to compute some things. So let's try to compute these. So let's see what the size of just AI is. It doesn't matter. Why call it 1? We'll call it AI because they're all going to be the same. So, okay. So in AI, urn I has to have 5 balls. So the very first thing I do is I give 5 balls to that urn. How many do I have left? I have 10 balls left. So I have 10 balls, 6 urns. Well, what I'm going to get, 10 balls, so it's going to be 10 plus 5. Choose 5, or just 15, choose 5. Okay. Now what about AI intersect AJ? And of course we have different ones. Not AI intersect AI, that would be cheating and we'd be back in the first case. Okay, what about the intersections where we have two different A's? What would the size of that be? Well, I'd have to give 5 to each of those first. So I give 5 and I give 5. And how many do I have left? I have 5 balls left. So I have 5 balls. I still have 6 urns. So I'm going to get 5 plus 5. Choose 5. Okay, now what about a triple intersection? AI intersect AJ intersect AK, where I, J, and K are all different. Okay. So, I have to give 5 to one, 5 to another, and 5 to another. There's nothing left. I'm done. There's only one way to do that. If I'm going to put 5 in urn I, 5 in urn J, and 5 in urn K. Okay, so now we get to use inclusion, exclusion to get our answer. Now, of course, the total number of ways we could just put balls in urns with no restrictions would be what? That would be the size of X. So that would be, well, 15 balls, 6 urns. So that's going to give us 15 plus 5, choose 5, or 20, choose 5. Okay, so let's put all this together. What am I going to get? I'm going to get 20, choose 5, and then I'm going to subtract off the number of ways that I can pick one urn. That's going to be 6, choose 1, times 15, choose 5. And now I have to choose all the ways I can pick 2 urns to be bad, to have too many. That's going to be 6, choose 2, and we have 10, choose 5 here, and then minus 6, choose 3, times 1. And that is our answer using inclusion, exclusion. Now, of course, the problem would be considerably harder if I had different upper bounds for different urns. I wouldn't be able to just say, hey, it's going to be the same for any 2 urns. And the problem also would be a little longer. I stopped here because I know that, if I tried an intersection of 4, I'd get all zeros. The problem would be slightly longer if this kept going because we had a larger number of balls. For example, if I wanted to do the same thing, let's just do it now. Let's say we have 20 balls, and still everything else is the same. 6 urns, they're distinguishable, and we want no urn, none can be greater than 4. So they all have 5 or less. Okay, so same type of problem. Well, now what would we get? We'd get for our size of x, we have 20 balls, 6 urns. That's going to be 20 plus 5, choose 5, or 25, choose 5. For the size of AI, and it doesn't matter whether I compute A1 or write AI, what am I going to get? I'm going to get, I have to place 5 balls, so I'm going to have 15 plus 5, choose 5. And IA intersect IJ, we'll assume that these are different numbers. We would end up with 10 plus 5, choose 5. Now my triples are going to be 5 plus 5, choose 5. And now we would add one more, and that would just be 5, choose 5, or 1. So we'd go one step further. So we'd get 25, choose 5, minus 6, choose 1, 20, choose 5, plus 6, choose 2, 15, choose 5, minus 6, choose 3, 10, choose 5, and then plus 6, choose 4, and that's 5, choose 5 there. And of course, you could imagine doing the same thing with more balls so that it gets to extend all the way out. It doesn't really matter. This sort of a problem, hopefully by now you can see how you would do it with larger numbers of balls. But like I said, if we were to include different restrictions on the urns, we could still solve this using inclusion-exclusion. But we wouldn't just be able to blindly say, hey, the intersection of any 2 sets is the same. Because let's say we have some urn that can't have more than 4 balls, and another urn that can't have more than 5, and another urn that can't have more than 6. Well, we'd have to deal with the placements in each of those situations. Even having something that's easy to keep track of, saying like maybe AI can't have more than, I don't know, I plus 3 balls in it. We'd have to do each of these intersections in a slightly different way, make it a much trickier problem. But okay, that's an example of how you can use inclusion, exclusion to do an assignment problem with balls and urns that we haven't seen yet. But there's still more that we're going to do with inclusion, exclusion coming up.